Okay, last time we talked about correlation. We had looked at that in a very limited context of retest reliability, but talked last time about linear correlation in a more general way as a statistical tool that measures the direction and strength of linear relationships between two variables. The extension of correlation analysis is regression analysis, and today we'll start talking about regression analysis. As an overview, in analysis of variance, and really in the context of t-testing and z-testing as well, we talked about independent variables and dependent variables. In regression analysis, independent variables are conventionally called predictor variables, and dependent variables are by convention called outcome variables. Again, the language of regression is different from the language of previous analyses that we've looked at. Independent variables are recast as predictor variables, and dependent variables are recast as outcome variables. A second general observation is that in regression analysis, just as in analysis of variance, you can include multiple predictor variables, and you can include multiple outcome variables. This was the case certainly in analysis of variance. We recognized when we looked at completely randomized analysis of variance that you could include 2 or 3 or 4 independent variables, and you could also include multiple dependent variables. Once you include multiple dependent variables, it simply is known as multivariate analysis of variance. The same is true in regression. Just as in the case of analysis of variance, we will look in regression at the simplest case, where you have a single predictor variable and a single outcome variable. But the logic of regression analysis remains stable even in more complex models. As I think I pointed out last time, regression analysis is often used in, for example, economics, where you use a series of predictor variables like the interest rate, like the rate of unemployment and so forth, to predict some outcome, annual growth in the economy. What you're doing in regression analysis is you're taking a set of known actual values to create a model. That is, if we look at the simplest case, where you have a single predictor variable x and a single outcome variable y, you take known x and y values that are paired. For example, the number of prior convictions and the length of a prison sentence. And you take case 1, and case 1 has had 2 prior convictions and the length of the prison sentence was 5 years. Case 2 has 4 prior convictions and the length of the prison sentence is 6 years. You have a series of known paired data points. That is, known X values and the associated known Y values. You use those known data to generate a model, a regression model. You can then use that model to predict unknown values of Y from known values of X. And I will again return to the example of predicting economic growth. You take known values from previous years of predictive variables like rate of unemployment, like the interest rate and so forth, and the outcome variable, growth in the economy. You then come to a current year where you know the value of the predictive variables, but you do not know the value of the outcome variable. And given the model that you've created based upon the known data, the past data, you can now use those predictive variables to forecast or predict the outcome value of the outcome variable, in this case annual economic growth. That's the general nature of regression analysis. I'm reminded of a line in a program called Elizabeth R. that appeared some years ago on PBS. 2 prisoners are taken into the Tower of London, which was never a good thing. Oh, going down the Thames, headed for the Tower of London, everything must have puckered up just a tad. You're taking me where? And the keeper of the keys comes in. They're now strung up to a wall in a prison cell, I don't know how many feet below ground. And into comes the, I don't know if he actually had this name, but the head torturer with all of his gear. And one of the prisoners pleads for a quick death. And the keeper of the keys says, "Death is always quick. It is sometimes the road to death that proves to be a little tedious." Well, summing up regression analysis can be done very quickly. It's getting to that bottom line that can sometimes prove a little tedious. So we're about to embark on the torture. Well, yeah, we in a cooperative way. There are 3 symbols that are relevant to regression analysis. X, and X is the predictive variable. Y, which is the outcome variable. And Y hat, Y with an inverted V over it, which is the predicted value of the outcome variable. Let me just go through that again. You have the X, the predictor variable. You have Y, the actual outcome variables. Together, these comprise the known pairs. In my example of predicting economic growth, this might be the predictor variable, might be the prime interest rate. The Y, the outcome variable, might be the rate of economic growth. And you have known pairs from previous years. And you use those pairs of scores to generate a model which allows you then to use these known values of X to predict unknown values of Y. Are there any questions to this point? Let's just take a very simple model. Let's presume we have 3 pairs of data. You understand that we can use those data pairs as XY coordinates in 2-dimensional space. Yeah. If X is the number of prior convictions and Y is the length of prison sentence, we could use those 2 data points to place that case in 2-dimensional space. Yes, we have an X coordinate and we have a Y coordinate. Let's presume that we have 3 data points. When X is X1, Y equals Y1. When X is X2, Y equals Y2. And when X is X3, Y equals Y3. Yes? So that these coordinates are in the first instance X1, Y1, in the second instance X2, Y2, and in the third instance X3, Y3. Yes? Are there any questions? Regression analysis requires that we generate the line of best fit. The line of best fit through these data points. More specifically, the straight line of best fit through these data points. It's evident that you cannot draw a straight line that connects each of these 3 data points. Would you agree? So the line of best fit, whatever that line is, wherever it runs, will not run through all 3 data points. Another way of saying that is the line of best fit will include error. Let me ask you, if I draw 2 straight lines, line 1 and line 2. Does one of these 2 lines describe the data set better than the other? Which is the line of best fit out of these two, line 1 or line 2? Would you all agree that line 2 is a line of, given the choice here, would be the line of best fit? Would somebody care to explain to me why? Doesn't matter how clumsily you do this. I'm not looking for eloquence.
I mean, it actually goes through some of the data points. Line 1 doesn't touch any of the data points.
Line 2 doesn't touch any of the data points either.
It's closer to it, though, than line 1 is. It's at least going...
Okay, that's a critical point. Although neither of these two lines actually go through any of the data points, both of the lines miss all 3 data points. Line 2 appears to be closer to those data points. And I think that's why each of you selected line 2 as the line of best fit given this choice. Would anybody care to recast that explanation? That is, recast the explanation of the line being closer to the data points, to recast that argument using the word somewhere or other, error.
Line 2 represents less error than line 1.
Would you mind if I said involves rather than represents? Line 2 involves less error than line 1. I'd go along with that. Would anybody care to now recast that argument using, rather than error, the terms predicted and actual y-scores? It doesn't matter. I'm out front peddling. You don't, you know, it doesn't matter. Let me start this explanation. When x equals x1, the actual value of y, you agree, is y1. Yes? We agree to that at the very outset. But when x equals x1, if we focus on line 2, the predicted value of y rather, is y hat 1. Would you agree?
For x2?
No. When x equals x1, the actual value of y is y1. But if we focus on line 2, the straight line that runs through here, when x equals x1, the predicted value of y is not y1, it's whatever this point is, yes, on the y-axis. And we can call that predicted value y hat 1. Y hat 1. Little hat. But not really a hat, because it's not really sitting on the head of the y. It's hovering just above, magically, the head of y.
It's always above?
It's always above. Y hat 1. When the value of x is x2, the actual value of y is y2. You would agree? But the predicted value of y, if we focus on line 2, when x equals x2, is some value around about here, right, which we can call y hat 2. Yeah? And when the actual value of, when the value of x is x3, the actual value of y, of course, is y3. Yeah. But the predicted value of y is somewhere in here, and we could call that y hat 3. Do you see that we can conceptualize this notion of error? And we got as far as that. We said that, first of all, that line 2 was preferable to line 1. It was a line of better fit because it was closer to the data points than line 1. We then moved to it involves less error than line 1. Do you see that we can operationalize the notion of error as the difference between y1 and y hat 1, y2 and y hat 2, and y3 and y hat 3? That is, this is error. This is error. And this is error. Those are the discrepancies between the actual value of y when x assumes some value, and given the line, the regression line, the line of best fit, the predicted value of y when x assumes that value. I have already reached a point where I think I'm talking in another language.
It's French class, right?
This is French, yes. Je m'appelle Mi. Are there any questions? Let me put it this way. What questions are there? Yes.
Is best fit the same thing as goodness of fit?
No. Goodness of fit is a notion that is used in another data analytic procedure. The line of best fit we'll move to here in a minute. We could sum this error together, yes? That is, we could add this distance to this distance to this distance. And that would equal the sum of the error that's involved in line 2. Would you agree? What I've darkened here is the difference between, first of all, the actual and predicted value of y1 when x equals x1, and the difference between the actual and predicted value of y2 when x equals x2, and the difference between the actual and the predicted value of y3 when x equals x3. This is simply the distance between the line and the data points. And we could sum those distances together as a measure of the total error involved in line 2. Yes.
The distance between the y values and the y hat values summed together equals the error? Or that
The difference between the actual and predicted y values is a measure of error? Yes. Are there any other questions?
The area of the x values to the y-axis, that's not the error, it's just up and... Does that make sense?
The error does not occur in the x values. You hold the x values constant and let the error accrue in the y scores. So that, as I've indicated, we could at the very least sum these distances, these differences together. And that would be a measure of the error involved in line 2. And we could do the same for line 1. Yes, when x equals x1, the predicted value of y here would be y1 up in here. That is, this would be the error in line 1 for x1. This would be the error in line 1 for x2, and this would be the error in line 1 for x3. Would you agree? And we could sum those distances together. And if we did that, we would discover that the error involved in line 1 was greater than the error involved in line 2. Which is why, when asked which is the line of better fit here, 1 or 2, each of you said line 1, rather line 2. Or what you had done in an informal way is what we have done in a more formal way. You said, well, line 1 is generally closer to the data points. And another way of saying that is it involves less error. And a third way of saying that is to operationalize what we mean by error. And what we mean by error is the difference between the actual and the predicted y value when x assumes a specific value. What we mean by error is the difference between the actual and the predicted y-score when x assumes a specific value. All we've done here, would you agree, is to sum together the difference between yi, individual y-scores, and y hat I, the individual predicted y-scores. One person saying either I'm giving up on this or I need a break. I sense a little confusion. Does anybody want to try and articulate that confusion? No? God. Yeah, that was a straight line. Let's go back to our 3 data points. Let's focus on what we take to be line 1. We know that the line of best fit is generated. We know that the way in which the line of best fit is generated has something to do with minimizing error. Would you agree? I think I have a phone call I need to make. I need reinforcements. This is, let me sort of take a time out here. This is not the easiest thing to understand. And it's not the easiest thing to understand in part because the logic of it is significantly different to the logic of data analytic tests like analysis of variance or t-testing or z-testing. Let me overview the process of generating the line of best fit and using regression analysis. First of all, the line of best fit is somehow associated with the line that minimizes the amount of error involved. And that error is the difference between actual and predicted y-scores. And we have, in an intuitive way, selected between 2 potential lines of best fit and chosen one and chosen it uniformly because it passed closer to the data points, it involved less error. That is, the sum of yi minus y hat I was less for line 1 than for line 2. So somehow, even intuitively, before I said anything, you knew that the line of best fit was associated in some way with minimizing error. Minimizing the distance between the line and the data points. We did that by simply minimizing the sum of yi minus y hat I. Let me tell you this, that if you use this as the criterion to generate the line of best fit, you can generate multiple lines that will satisfy this criterion equally well. That is, you can draw multiple lines through this data set, through these 3 data points, all of which have involve the same amount of error when error is defined as the sum of yi minus y hat I. The first task then is to generate the line of best fit. How is that line generated? By invoking what is called the least squares criterion. the least squares criterion. This is an $80,000 piece of information. The previous $80,000 piece of information here was central limit theorem. Because central limit theorem, I hope you came to realize, underwrites all of the data analytic tests that we've looked at previously, because it allows you to invoke this theoretical notion of a sampling distribution of sample means, or a sampling distribution of sample mean differences. And you know a great deal about that distribution. You know its mean, you know its standard deviation, and you know that it's normal. What underwrites regression analysis is the least squares criterion. And it underwrites regression analysis because if you invoke the least squares criterion, you will be able to generate a single line that satisfies that criterion better than any other line. And the least squares criterion requires that you minimize the sum of yi minus y hat I squared. The least squares criterion requires that you minimize the sum of yi minus y hat I squared. That is, rather than add these differences together as we did initially, what you have to do is square those differences and then add them together. That's all. The least squares criteria requires that you minimize the sum of the squared differences between the actual and the predicted value of y. It requires that you minimize the sum of the squared differences between actual and predicted values of y. Let me say that again. Just in case it's on an exam. It requires that you minimize the sum of the squared differences between actual and predicted values of y. In reality, you clearly do not have to sit there drawing an infinite number of lines and computing the sum of the squared error between actual and predicted values of y and then choose a particular line. This is simply part of the software that allows you to generate the regression line. And this is the regression line. This is the line of best fit. Yes. That this criterion allows you to generate the regression line, which is the line of best fit. Okay. The least squares criterion requires that you minimize the sum of the squared error, or the squared difference, the squared error between actual and predicted y-scores. The least squares criterion requires that you minimize the sum of the squared error between actual and predicted y-scores. That is, rather than simply minimizing the sum of this error, you square these differences, you square this error, and then you sum it together. That is the least squares criterion. And by invoking the least squares criterion, you can generate a single line through these data that minimizes that value better than any other line, better than any competing line. That is, it allows you to generate the single line of best fit. People are covering their eyes, they're holding their heads. They're putting their hands over their ears so that information doesn't escape. They're in prayer that sooner or later this meeting will come to an end. It's sometimes the road to death that proves tedious. You just got to hang on. I'm going to go over this stuff again. At the moment, just let it roll over you. If at the moment it's not all there, I wouldn't worry at all. Fundamentally, we've said something very, very simple. We said, first of all, that any straight line that you draw through this data set will miss one or more of the data points. That is, the line will involve some amount of error. And we've extended that notion to the least squares criterion, which is a statement about how you generate the line of best fit, the single line of best fit. And it, as we imagined, as you intuited at the very outset, it's a line that somehow minimizes the sum of the error involved. It's simply not the sum of the error, it's the sum of the error squared. Easy. Nolo problemo. Let me ask one more question before we bring this carnival to a close. But just for today, we'll be back for another show. What is the form of the equation that describes this line? You've got to go back into the archives for this one. You've got to blow dust off of some stuff. What is the form of the equation that describes this straight line?
The answer is in the question.
What is the form of the equation that describes any straight line?
Linear.
Pardon?
Linear.
No. Pardon? No. No.
Y equals like AX plus B or something?
Oh man. Y equals AX plus B. I think that's how you folks say it over here. In the old country, we said Y equals A plus BX. The form of an equation that describes any straight line is y equals a, some constant, plus bx. Tell me, in general, what is the value of a? Or you can tell me what the value of b is. You don't have to give me I'm not looking for a number here. I'm looking for what it is.
Would it be your predictor value?
No. Not a predictor value.
Non-imaginary.
Non-imaginary. It's not non-imaginary.
Well, for the dx, shouldn't b be the rate of regression or aggression?
The rate of regression is b. I think there's an easier way of saying. I know there's an easier way. Oh, we are starting to fire on all jets, aren't we? Isn't it invigorating when you discover that something you learned some while ago, it's useful again? B is the slope of the line. So what's A? A is the y-intercept, see? A is the y-intercept. This value here is A, where the regression line intersects the y-axis, and B is the slope of the line. Woo! I feel a sense of exhilaration. I feel like, in the Tour de Research Methods, we've just gone up Alpe d'Huez and we're still all together. This stuff is easy. This stuff is easy because it relies on a logic that I presumed you learned somewhere back in, I don't know what grade. Y equals A plus bx, where A is the y-intercept and B is the slope of the line. This is a giveaway. It's all downhill from here. Yeah? The torture's over. It's the ride up Alpe d'Huez that's painful. The ride down Alpe d'Huez, you just have to make sure that you don't go over the edge, get carried away and out into space. Good things don't happen usually when you go out into space on a bike, even if you're wearing a helmet. So we will continue to talk about regression analysis next time.